Right, so the question is, do we really need PTP? And to answer these questions, I'm going to compare the clocking and synchronization of various, streaming methods, streaming solutions. And yeah, well, let's jump into the topic. I don't have to introduce myself anymore, I guess, so I'll skip over this introductory slide. And just as an introduction to the topic, let me replay, so to say, or recall the general requirements we have when we look at audio distribution over networks, what we really want to achieve. I'll do this a quick one because I have that a bit more on detail in one of my previous presentations today. So we want to have media bit transparency, right? So no sample rate conversion is to be employed, and that all means that all streams, sender and receiver, need to run on the same media clock, because if they are not, we would have to use sample rate conversion. Also, if we have a network, we don't want to stick to 48 kilohertz for the whole network. We want to run different sample rates on the same network at the same time, even if a particular transmitter and a particular receiver can only work together on the same frequency, right? So we want to have a low latency on the network, and we want to have a determinable. So we want to have a deterministic playout so that we can align different media streams sample accurately on the network. Here's an illustration. Oh no, sorry, the illustration is coming up. Once we have the network in place, we don't want to have the green cable running around the venue with the house clock distribution anymore, of course. And all these requirements result in that we cannot work with asynchronous streaming. That means that clocks are reassembled from incoming streams. That's the asynchronous case. We cannot just work with the distribution of master clock beats without time reference. That's what we call the synchronous case. That's with the house clock. The house clock case is the synchronous case, right? We have frequency, but we don't have time. We actually want to have the synchronous case in these networks, and that requires that all devices have the same common understanding of a reference time or a wall clock. We all know from, well, if we are in media business, we all know that audio applications have the highest accuracy demands when it comes to timing and precision. And one of the requirements is sample accurate alignment of different streams coming into a one or other multiple receivers. So that means we have to have an accuracy of plus minus half of the sample frequency or half of the media clock, right? Otherwise we won't have any sample accurate alignment anymore. So here's the example I was referring to. We have a transmitter. That one is providing a sample to the network. We have a receiver. That receiver clock is off by half a sample period, which would mean that the sample on the time plane is situated like this. We may have another receiver which is off half a sample period in the other direction. That sample would then be located here, and if we compare the total difference between receiver 1 and receiver 2, it should be less than one sample period, otherwise we won't play out the same sample at the same approximate time, right? So that sample accuracy requires half a sample time. That translates, when we do the math, at 48 kilohertz and a time precision for our wall clock of plus minus 10 microseconds at half a sample rate at 48 kilohertz. And if we go higher, it's even smaller number which we need from the wall clock. Then also we want to get rid of the screen house clock cable, and when it comes to distribution of word clock reference, we are in the AES11 master clock specification. Right, and that calls for plus minus 5% maximum jitter and wonder. So we need to meet even tighter restrictions or constraints. If we have a transmitter and a receiver, and that particular receiver or any two receivers compared with each other, we need to have plus minus 5%. That's 0.05 of the clock period where the phases need to align. Otherwise, we can't match AES11 for master clock requirements. So that translates into timing. At 48 kilohertz, the accuracy we need is plus minus 1 microsecond. So the whole precision we need, the whole accuracy we need from our timing system would be plus minus microsecond at least, if we want to achieve AES11 accuracy here. Now, let's directly jump into how do different streaming solutions or methods actually work. So we will compare the plain RTP streaming just based on RFC 3550, that's the underlying standard for it, with AES67 and 2110 because they use the same mechanism. We will have a look at AVB TSN, how clocking is achieved there, and also on the new thing on the horizon, the IPMX, the IP Media Experience definition, currently being worked on within AIMS, VSF, and other organizations. So let's jump right into the RTP RFC 3550 definitions. We look at the generic RTP clocking for linear PCM audio. So we are distributing a stream, linear PCM audio, with no wall clock at all, right? So we're just sending that off on a sender to a receiver, and the sender then has either a free running internal clock or is synchronized with an external media clock which relates to the media which is being sampled. So the media clock, either the free running one or the externally fed media clock, is the reference for the media clock sampling, that drives the sampling. Once we have a packet ready, it is sent over to the receiver with what we call the RTP clock inside, but the RTP clock in fact is actually following the sample clock or the media clock. So basically that's pretty much the same, except that RFC 3550 recommends not to use the same media clock counter for all the streams in a network, but recommends to use an individual random offset to the RTP clock, so that when you use encrypted streaming, you don't know a particular value inside the encrypted range. So if it would be 0 for all streams, so no clock offset, you would know a particular value inside the encrypted portion of the RTP stream. And so that's why the RFC 3550 folks recommend to use a random value. However, that doesn't matter in our case, because not doing any synchronization at all, except that the receiver is now getting the data in, and it needs to try or needs to reassemble the original clock by observing the incoming stream data, right? And one method of doing this is with the adaptive playout algorithm. So it's basically waiting until the receive buffer is filled up to a certain amount, let's say 50%, and then it starts playing out and it observes the fill level of the buffer. If it's playing out too fast, it's slowing down the playout media clock. If it's because the buffer would run empty, right? If it's playing too slow, the buffer would fill up and it's accelerating the media player. So it's an adaptive media clock regeneration to match approximately what the sender, and over time exactly matching what the sender has been used as media clock. So basically the playout is triggered by the media clock, and the media clock is adjusted by observing the fill level of the receive buffer, right? That's one of these generic schemes you can do to recover the media clock of the incoming streams. There are also other ways of doing this. This is one way. Now, if we have the ability to feed an external reference to the devices, just a summary of the main benefits and drawback of this particular scheme. So we can use, the benefit definitely is we can use any input, any media clock that and can resemble the media clock on the output side, right? So we can have any particular source, and the receiver just looking at the stream, and it can resemble the clock. And of course, the quality of this resembled or recovered media clock depends on filtering, clocking circuitry, and so on. But it can be done with any input clock. However, I don't have the ability to concurrently process independent media streams because their clocks are not synchronized. In order to do so, I will have to employ sample rate conversion, right? Because I can't match two streams, the output of two streams, if they don't have the same media clock, right? So that's certainly a drawback. And since I only have frequency, I have no clue at what particular point in time a sample has been generated, and thus I don't have any deterministic latency, because I'm just seeing samples coming in. I know a bit of my internal buffer, but I don't know how long this sample had been on the line and when it has been generated. So I have no deterministic latency, and that does mean that I don't have a sample or any sort of alignment between streams other than just, okay, lock now and then play out. But I have no clue how they are being locked with respect to each other. Now, the traditional case is I'm feeding an external house clock around so that all my devices run on the same media clock. So that means I'm feeding the reference clock with the green cable, and that in turn means that the external input on the sender side is not, well, that's the external input basically actually, and then the media is sampled with the external reference clock, which is also fed to the receiver, right? So the receiver does not have to use this adaptive mechanism for recovering the media clock anymore, because it can rely on the externally referenced media clock, and so the playout is stable in terms of media clock frequency. So the benefits of this are that all media clocks are following a common reference clock, of course. That means that also the same media clock is used for all streams. That makes, in turn, it possible to have concurrent processing of independent streams, but they still have and don't have any phase and time alignment. So I just don't know how they have to be aligned in order to, to match the same sample or the same content, because still I don't have any means of time. And again, with that, I don't have any deterministic latency at the end. Of course, I can always, by looking at the content, try to adjust these. This needs to be buffered a little bit longer, or this needs to be played out a little bit faster, earlier. But other than that, I don't have any deterministic means to actually align streams. Now, a third method with RTP clocking is with employing the so-called real-time control protocol sender reports, which basically can work with a common reference clock or without a common reference clock. And since this is the basic underlying case for IPMX, I will cover this when it comes to IPMX, right? Okay, AES67, we can make a quick run through that because I mentioned that several times earlier. AES67 is based on the fact that all nodes are running local clocks which are precisely synchronized to a common wall clock reference utilizing PTP. And once those clocks are locally synchronized, they can generate any media clock I like, and since they are synchronized clockwise, they have the same media clock even in phase with each other, right? Here's the diagram to that. We have a master clock that may or may not be referenced to GPS depending on the use case, but all the slave nodes, all the slave clocks inside the devices are perfectly synchronized using PTP. And as you have learned earlier today, that can be as precise as 20 nanoseconds, right? So that's way below what we actually would need for phase accuracy according to AES11. So once we have the time, we can generate the media clocks, and if we put those media clocks, shift those media clocks above each other, they are perfectly aligned and in phase and in sync. So then we need the synchronization and clocking system. We have a sender, we have a receiver, we have the wall clock, we have the local clocks in the devices. They are synchronized by PTP. The media clock is generated out of the local clock, both on the sender and the receiver side. And I use that media clock on the transmitter side to generate the RTP stream and the RTP clock. Here's the RTP clock. And again, we can still use the random offset recommended by RFC 3550. We only will have to know this offset now on the receiver side in order to perfectly align those streams. And we don't do that in band with the RTP data itself. We do it out of band with an STP transfer. So the STP carries not only this offset information, but also other vital information which is required for AES67 anyway, like the payload format, the reference clock information, and so on. So that information has to be passed over anyway, and the random offset, if there's any, is also part of this STP record. A slight deviation is with 2110. 2110 looked into this random offset and they said, oh, we don't see a need for a random offset. We can live with a zero offset, so they require that a zero offset is being used instead, following the recommendation of RFC 3550 to use a random offset here. So that's basically the principle, how everything works in AES67 or 2110. And then the secret behind the deterministic latency and the perfect stream alignment is the so-called link offset, right? Here's the model again. We have the AES67 sender on the left side. We have the receiver on the right side. We have the network in between, and what is important are the ingress and egress reference points now. The ingress reference point is that point when I acquire a sample, that point in time. That point in time is actually sampled with the RTP timestamp in that packet. I add the link offset to that particular timestamp. I have to account for the random offset if there is any, and then the receiver exactly knows when a particular sample with a particular timestamp has to be played out. Right? The time needs to be, link offset of course needs to be large enough that it should not be played out before it even arrives, but it has to be small enough to not overload the receive buffer. These are the constraints, but basically this is how I can achieve a perfect aligned play out on the receiver side, and not even on one receiver, but between any and all receivers and any and all streams which are currently running on the network. So the benefits, of course, is all media clocks are following a common reference, and thus I have an absolute accurate reproduction of the reference clock in all nodes and identical phase and media clocks for all streams, just by utilizing PTP the way we do it here. That enables concurrent processing of independent streams because they're all on the same media clock frequency by design. I have an absolute deterministic latency, sample accurately. Alignment of streams is possible with that. And the drawback is, with AES67 or 2110, I have no chance of transporting asynchronous input signals on the network without using SRC on the sender side, right? Because I don't have the ability to send a stream which is not referring to the reference clock anymore. Like if I have 48 kilohertz reference clock derived from PTP, and now I have an asynchronous input signal like 47.9, there's no chance to bit transparently transport that on the network anymore. So the asynchronous case is definitely lost in AES67, except I'm using SRC on the input side so that I have a perfectly aligned stream again. Okay, that's AES67 as we know it, RAVENNA 2110, all the same, based on PTP as the reference clock. Now let's have a quick look into AVB or TSN. How does that work? Because we know probably already that AVB can transport asynchronous streams. Okay, here's a picture of a typical talker. They call the sender talker, that's their slang. Now, the first thing we need to look at is that audio is sampled with an external reference. So basically, the audio clock provided by the input signal, right? We don't have a reference clock, a frequency-wise clock from the network. It's following the input reference from the input media, just as the asynchronous RFC 3550, right? Same case here. However, the difference now is whenever we take an input sample, we timestamp that with a reference time, and this reference time is synchronized by, guess what? PTP. And since it's a layer 2 solution, AVB or layer 2 method, it's GPTP. So it's layer 2, it's PTP running on layer 2 instead of layer 3, but it's PTP. So AVB involves a reference, a common reference clock, except that it does not generate the media clocks from that reference clock, but uses the input media, the inherent input media clock, and timestamps the edges when samples are taken with the reference time. So what happens is, if I look at the outgoing stream, the P7022 stream, it's a layer 2 stream, not RTP, it carries the data, the sample data, and for a number of sample data, which is defined by DBC, which is similar to the packet time in RTP, we have a timestamp for the first sample there. So in other words, if I look at these streams, I exactly know when samples have been taken, at what reference time they have been taken. Now the task of the receiver basically is, it has to rebuild the input media clock, right? And for that particular reason, it is looking at the timestamp values of consecutive data packets. And by comparing this against the PTP reference time, it exactly knows, okay, within, let's say, 12 or 48 or whatever samples I have here, by just doing a simple math, it can exactly tell you how many clock periods, or in what time a defined number of clock periods has to be generated in order to then play out the media. So from the combination of the number of samples in a packet, marking the number, the number of clock cycles which have happened between two exactly known timestamps, I can regenerate, well, the number of clock samples I need to generate in that particular time. Like this, okay. Sorry. Right, so, and then of course the samples are depacketized themselves and played out with the just regenerated media clock. So I have a perfect case of transporting asynchronous media, but with timestamps which are coming from a reference clock. And the receiver does not have to play any tricks at all, it just has to follow the reference clock and the number of samples in the packet. And so the main benefits for AVB is we have variable input clocking. We can use any media input clocks we want. The receiver always can perfectly resemble that media clock. We have a deterministic latency. It's called presentation time in AVB. So I mentioned the precise reassembly of the input media clock. And the drawback is still, as with RFC3550 asynchronous case, concurrent processing of independent streams is not possible, because that would require, again, a second, media clocking stage in the receiver. If one input is running at 47.9, the other at 48.01 or whatever, the receiver can reassemble each of them independently, but not both of them, right? Because it can only run on one clock. So that means no concurrent processing of independent streams, but at any point in time, point to point is always very precisely possible. If I want to achieve system-wide synchronization with AVB, I would have to run a reference stream around, right? In addition to the clock I already have, I would now have to tell all the participating devices, okay, here's my reference clock. That does not have to be exact 48 kilohertz, it can be anything, but I have to run it around and tell the devices, you're not observing your input media anymore, you have to follow my reference stream. So it's a dual-staged media clocking, while AES67 is directly deriving the media clock from the reference time. So, but basically that's working, and that's what's going to be used in Milan. So, finally, looking at IPMX, which partly is promising we can work without PTP and with PTP. Let's have a look. What is IPMX? IPMX is an initiative by AIMS, but is also supported by VSF and AMR and other organizations there. The main standardization is executed by VSF, Video Services Forum. IPMX defines a set, well, I have to read that, of common, ubiquitous, open, standards-based protocol for interoperability over IP for the Pro AV industry. I can't remember this, so sorry for reading this. Basically, IPMX is based on the proven SMPTE2110 standard, but it is enhanced and adopted for the specific needs of Pro AV applications in terms of providing enhanced or relaxed timing requirements, supporting any bit rate, also with compressed and uncompressed streams. It's video format agnostic, it has HDC copy protection, stuff you usually find on the HDMI source side of things, right? So there's also I/O and edit data and all these kind of things. All this needs to go into IPMX if we want to transparently transport HDMI input signals with IPMX. So, and the goal is, at the end, simple deployment requiring only basic knowledge of the network itself, right? That's the key idea. That doesn't mean that the manufacturers who build IPMX devices can do it just very easily or don't have to have any knowledge at all. But the idea is, once the IPMX devices are there, it's not that much of an effort anymore to deploy them on the network. At least that's the idea. Let's take a further look. How is the clocking and synchronization done in IPMX? So IPMX, if someone was here when Sam from NetworX presented yesterday, IPMX strives to support the full range from professional live system, large systems, synchronous, asynchronous systems, down to one-to-one connection between HDMI sender and an HDM receiver, just an input signal to a monitor, something like that. In the broadcast application field, usually you have those devices being locked to house sync or operating in a 2110 or AES67 mode anyway, so we have the synchronous or at least synchronous operation. And in a non-broadcast operation, you might see these cases as well, but more commonly you have asynchronous signal transport, right? Because you don't require the overall system synchronization at all. So there's the lack of this common reference clock, usually. Now, IPMX says it supports networks with and without PTP support. When there's PTP available, it specifies what devices have to do, well, when PTP is present. But they also specify what IPMX devices have to do if they don't have PTP present on the network. So that's basically what's in the specification, and it says also the devices need to support both modes. So even if the goal for IPMX is to work on networks without PTP, the device implementations always need to be able to work with PTP. There is no such thing like, I build an easy implementation in my device and I don't care about PTP. If you build an IPMX device, it has to play with PTP. So, if we further look into the existing current drafts, and they are still evolving, we may find some confusing aspects there. One hand it says PTP shall be supported. On the other hand, it says it's not required. But as I pointed out earlier, that does not relate to the implementation of the devices. It has to be supported by the implementation. It just makes up the case that there might be no PTP present on the network where they are operating. Then all IPMX receivers should be able to recover any asynchronous input signal timing and produce an output signal that is frequency locked to the IPMX sender. Well, that just basically means RFC3550. I feed a signal in, and at the end I want to be able to get it out. Or the AVB case, which also is the asynchronous input signal with a common reference clock, right? The problem is that these mechanisms are not really described in detail. So it leaves it kind of open how this should be achieved. Which, you know, I mean, if you dig into the development, this is not a big problem because you can imagine how this is done. You only have to make sure that all devices do it in a similar way, otherwise interoperability is endangered, right? And then they have some ambiguous statements or requirements on stream alignment, and we will see in a minute why. Mainly they refer back to the link offset, which I have explained for AES67 in SMPTE It's called delay L or DLO, which is basically AES67 link offset. But that only works if I have a common reference, right? Because it has to have a reference time. IPMX says it's also working among streams originating from the same sender. If no reference clock is present, well, question mark here, but that's probably where the definitions have to be more precise and have to be refined. So let's look into these three different cases. SMPTE2110 is as easy as well, the synchronous mode, we have covered this. Then we have the asynchronous operation, the pure asynchronous operation. That could be achieved with the previously explained RFC3550 asynchronous operation, right? Input signals are asynchronous, internal clocks are synchronized to a common reference clock. Or with a common reference clock, right? And that requires this RTCP sender report with timestamp pairing. I delayed this from the beginning to now because by now we know from the AVB side of things how this actually works. We have an asynchronous input clock, and similar to the AVB operation, what we do now is we replace GPTP with PTP, still reference clock, wall clock time. We replace P7022 data with RTP data, and we replace this timestamp generator with the RTP timestamp generator. And what it actually does is it's generating RTP packets which have this RTP timestamp and the payload data in here. So the payload data comes from the sampling stage, and the RTP timestamp comes from the adjacent RTP timestamp generator. So we essentially put in the reference time for a particular sample into this RTP packet. Now the second thing we need is the sender report. It's not the same packet, it's an RTCP packet. And that basically has a time pair of the clock reference time and the time when the sample in that packet has been gathered. So I have a timestamp pair which relates the input time of the sample to the wall clock reference. And it's pretty much the same operation as with AVB, except that at the end I don't have one outgoing stream, 7022, I have the RTP stream and I have the RTCP sender report streams. So in other means the IPMX node has to support RTP streaming with paired RTCP stream in order to achieve this paired timestamp operation. So that's pretty much the same as with AVB, and then we have the already explained asynchronous case without the common reference clock, although IPMX is not very explicit on this, how this actually should work. It's still requiring this RTCP reports, but it's of no use, right? If I don't have a reference clock where I can take my reference timestamps from, what's the use of it? And actually, RFC 3550 says, well, if there is no common reference clock, you may also leave this field empty or filled with zeros. So that's something IPMX definitely needs to dig in a bit further and refine the specification from where it's standing right now. Then it can come to an interoperable solution anyway. So in summary, IPMX is trying to incorporate all the three clocking modes we have learned about in one method, in one system, into the IPMX system. The fully synchronous operation of AES67 and 2110 with a PTP common reference clock. Also the AVB-like timestamping operation just with RTCP sender reports, right? And this RTP generic clocking of a full asynchronous stream without any clock reference at all. That's what they try to incorporate into the standard. So coming back to the overall question, do we really need PTP? Any thoughts, any hints? Who thinks that we need PTP? Who thinks that we don't need PTP at all? Well, nobody. Okay, summary, PTP enables very precise clocking, transport of synchronous and asynchronous input signals, perfect alignment of any streams anywhere in the network, but most likely require a more complex network design to make sure that the PTP traffic actually is transported in a way that I have a precise and accurate clock synchronization anywhere in the network. That depends actually on the complexity of your network. If you have a small, easy network setup, that's no big deal running PTP to the required precision through the network. If you have a complex corporate environment, there are some challenges, but believe me, it will work. It requires knowledge, definitely. Well, without PTP, we probably have a far or at least less complex network design, right? We don't have to worry about PTP at all, but we have no synchronous operation at all. All streams, all devices operate independently from each other. And I can't align any two streams with each other. So the question is, functionally, from a functional point of view, I clearly have massive advantages by using PTP. And in most cases, I probably need the benefits offered by using PTP as a reference. From an ease of use point of view, well, that goes to the other side. I probably just don't care about all the requirements, the precision, accuracy, alignment. I just want to transport signals, and I don't care what other signals are doing on the network. I have a transmitter here and my reception point there. Why would I use PTP at all? So there's no clear answer to this question, but these are the differences when you use PTP or have PTP available, and if not. Any questions here? No? As always, there's the URLs to the resources. RAVENNA website, AIMS website. IPMX has its own website, which I forgot here, IPMX.io, very easy to remember. And well, in case anything is left open, just shoot me an email and happy to discuss any further. So, your flight was delayed by 4 minutes. Less than the last presentation I had. Thank you very much.